Most people know of the Schwarzschild radius in the context of black holes. There are many ways to define what the Schwarzschild radius is, but I think the easiest way is as follows. We could say that the radius at which a mass has an escape velocity equal to the speed of light is called the Schwarzschild radius. And any object smaller than its Schwarzschild radius is a black hole. This is because we will need something to travel faster than light in order to escape it, making it invisible, hence the black in black hole. We can calculate the Schwarzschild radius of any object, and once we get that object to have a radius smaller than that of the Schwarzschild radius, it becomes a black hole. The Schwarzschild radius is exactly the same as the gravitational radius, just a different name describing the same thing. For a more technical definition, the Schwarzschild radius or the gravitational radius is a physical parameter in the Schwarzschild solution to Einstein's field equations that correspond to the radius defining the event horizon of a black hole. The event horizon is just the boundary where the velocity needed to escape the black hole exceeds the speed of light. So that's the point of no return that you hear people talk about with black holes. Once you get past that, even if you're a beam of photons traveling at the speed of light, you can never get back out. As I mentioned a short while ago, the Schwarzschild radius is a characteristic radius for any object with mass, so basically anything except a photon and maybe some neutrinos. But for anything less than the most massive stars, this radius is going to be very tiny. You can actually calculate your own Schwarzschild radius using the Schwarzschild radius equation, and you can see how small you'd have to be to become a black hole. Something that isn't so well known is that the Schwarzschild radius only applies to Schwarzschild black holes. A Schwarzschild black hole is a black hole that has no charge, no angular momentum, and it's spherically symmetric. Basically the simplest kind of black hole you can have. Such a black hole is described by what is known as the Schwarzschild metric, and such a black hole can't be distinguished from any other Schwarzschild black hole other than by its mass. That's basically because it has no other parameters. And a metric is simply a framework used to describe the geometry of space and time. The Schwarzschild metric is also a good approximation for describing slowly rotating astronomical objects such as slowly rotating planets and stars. Such approximations are necessary to prevent calculations from becoming overwhelmingly tedious or nowadays computationally expensive. There are other metrics to describe black holes too, and these metrics are necessary because in real life black holes aren't static, they have charge. So we have the Kerr metric, which is a generalization to the rotating Schwarzschild metric, meaning it still has no charge, now it just rotates. It's got angular momentum. The Kerr metric is an exact solution of the Einstein field equations of general relativity. However, these equations are highly nonlinear, which makes exact solutions very difficult to find. Then we have a metric for a charged rotating black hole known as the Kerr-Newman metric. This was discovered shortly after the Kerr metric. And one thing you'll find which is quite common in physics or mathematical physics in general is that generalizations always come later. You have a specific use case of an equation, such as the Schwarzschild solution, and then later on you build on top of that to allow for more and more cases. So the Schwarzschild metric applies to one case, and then you have the Kerr metric, which applies to a few more cases, then you have the Kerr-Newman metric. And the same thing happened with relativity. Special relativity came first, where gravity wasn't included, for example, and then later on you have general relativity, where you have more cases, where gravity is one of those additions. Going from a special case to a general case is quite a tricky process. That's why it took decades to go from the Schwarzschild metric to the Kerr metric, and why it took many years to go from special relativity to general relativity. But as always, these things are born out of necessity. So, of course, black holes are a super interesting topic. I have many links and references to what I talked about in this video in the description below. I have my Twitter, TikTok, website link in the description also. If you want to ask any questions, the comments are free, as is my Twitter. So I guess I'll see you next week for another episode of me talking about astrophysics.